Hi everyone. With this video, I wanted to explain to you how to automate driving. So basically the building blocks to make a car drive itself. That's something that we've been wanting to discuss in class already for the last sessions, but we never got to it because we had great discussion around many other topics. So with this, I hope that you can develop a better understanding how to make a car a self-driving one, and there will be a lot of information, and you might want to stop at any time and maybe just look at the slides. If you want to go back maybe to listen to my narrative again, then that's very convenient, obviously, in a video. And certainly also you can just reach out to me and ask, what did you really say there? And I don't get it. So more than happy to explain further and certainly have a discussion and to get your perspective. But to get started, what I want to do, give you a little bit of an overview, how an automated car works in general, then certainly talk about sensors, the software, but also about the infrastructure, what's needed maybe around the self-driving car in order to make it work in traffic in general. Then a little bit of a summary outlook, which actually is more like what's missing, why are we not there yet? Let's dive right into it, into the overview. So this is a depiction of a self-driving car, if you will, and you see here with all the numbers, quite a few sensors, GPS technology, maps, but also a few other sensors, and then some user interface, certainly a CPU, a central processing unit, and then steer-by-wire, brake-by-wire, drive-by-wire. So basically how an automated car would work. So the user enters a destination here with a touchpad or whatever. I want to go to San Francisco Airport. Oops. And then there's a map in the vehicle that basically knows how to get from your location to San Francisco Airport. That's very straightforward, same as a navigation system, basically. And then the vehicle basically knows where it is through GPS, IMU, inertial measurement unit, so it senses the motion of the vehicle and it knows how much the wheels are rotating, so the distance that you're traveling. With this, you could basically talk about the route, where you want to go. But guess what? There are obstacles, dynamic objects in the way of the vehicle that you detect with maybe laser technology, with cameras, or with radar up here. And they basically tell you there's something in our way and we need to react to that. So we need to do a maneuver around those obstacles and still stay on the road. And this then becomes some sort of tactical path planning, which is still something, yeah, you want to go around this object, this obstacle, but do you want to take a wide swing around it so that you might end up in the adjacent lane, or do you want to slow down and maybe pass more the narrow trajectory through that object? So that's some planning that needs to be done. And then basically, once you got all of that figured out, you can send your signals to electrified steering that basically every vehicle has today. Electrified braking, every vehicle has that today. And also the powertrain is basically electronically controlled so that you can just send those signals there and then you can go around an object, slow down for an object, or maybe accelerate to actually get to your destination. And you might also want to exchange some information with other people in the vehicle or around the vehicle. So, which can be anything like an announcement, but also turn signals, brake lights, and all of that. So, very straightforward, but what's actually needed? So let's talk about those sensors a little bit more because those always come up. And just for context here, modern high-end vehicle has about 20 plus sensors. You see here on the side, laser scanners are making inroads, a lot of radar camera technology, 20 plus in total. Similar Tesla Model 3, Model S, X and Y, they have about 21 sensors. Also, you see cameras, radar, and we'll talk about LiDAR in a minute if that's needed or not. Waymo's early program vehicles or research vehicles, I'd like to call them, have about 40 sensors. So they have a lot of these LiDAR, which is laser scanners. So all that's in blue. Quite a few cameras, that's in orange, and radar technology as well, what you see in green. And in an, again, high-end production vehicle, let's take the Audi A8, you find many of those, ultrasound even camera, radar, and LiDAR technology. And here's a little bit of a price point. Ultrasound, relatively inexpensive, and you see here what those are being used for forward collision warning, parking assist, blind spot detection, things like that. There's quite a bunch of cameras. I'm not saying that all of those are actually in an Audi A8, but that gives you some perspective or the different kind of cameras that they are. They can cost anything between $10 and $70, give or take. Radar cost has come down significantly. When radar technology was launched in an automobile, it was more like $1,000 a piece. So now it's come down to 50, higher end, maybe $80, something like that. Top of the line these days is LiDAR, so laser technology that costs several $100s because it's still early technology, and cost is expected to come down as well. So what about camera, LiDAR, and radar? So let's look at how those work and pluses and minuses. Camera needs some ambient light that actually gets reflected by an object and then is processed in an imaging sensor. And the good thing is cameras also do color, which none of the other sensors do. They are relatively good to classify an object. They can say, I see a car, I see a truck, I know where the lanes are, but they don't work well in bad weather. They don't know much about the velocity that a vehicle is moving and also the distance. They are not very good at this, which is what radar does very well. Radar sends out this radar pulse, which becomes sort of like a fan-shaped signal, and then the reflection comes back. From this, you basically know with time of flight, as it's called, what the distance of that object is. So it's very, very good at this. Also in bad weather. Bad weather is heavy snow, rain, dust, no problem for radar. And so it gets very good information of where an object is, but not so much actually what kind of object it is, and where the lanes are doesn't get you really much. And angular resolution basically means it knows that something is within this fan, but is it like straight forward or 3 degrees to the side? It doesn't really know, and obviously it does make a big difference if something is 100, 200, 300 feet out from the vehicle. Gets us to LiDAR technology, which is sending out laser beams on a rotating basis, and gets a reflection back into an imaging sensor, so somewhat similar to camera and radar, so somewhat in between, which means it's very good at detecting an object, its distance, and also exactly under which angle you see it. So it's very precise, but it doesn't really get the lanes that well. And it also is not that good in heavy rain or snow, so bad weather, and not really ready for production. So this is what you saw on a relatively high price point. So those need to mature still a little bit more. Basically saying all pluses and minuses, as you can see. And yes, I know Elon Musk is basically saying LiDAR is a fool's errand. Anyone relying on LiDAR is doomed. Let me repeat that, doomed. And he says it's not necessary. And he's somewhat alone with this in the industry. There's certainly others who say it's fundamentally unsafe to only rely on radar and video. And let me say this is for higher levels of automation. So for level 3, level 4, level 5 that we talked about. For level 1, level 2 systems that we have on the market, they have their own limitations, largely due to the fact that the sensors are not as powerful, but the driver is still in the loop. But if you want to take out the driver, then I do agree with Luwai Alada, the CEO and co-founder of Quanergy, which, okay, fine, is a laser sensor company. But I agree that you would need it, and because otherwise you cannot really differentiate between what is a human and what is inanimate. And same here, also another LiDAR company from Velodyne. They also said Elon Musk is great, but quality and safety is maybe not what he's necessarily known for. Well, a more established player, interesting. Nissan basically says here with a general manager of advanced technology development, it'll be fantastic to have LiDAR, but it's not ready. So that's maybe one of the points why we are not as far along with really self-driving car as we had thought, because there is this understanding we need LiDAR, but it's not ready. So laser technology being necessary, but not really ready. And here just one other example. Mobileye is really known for a very camera-centric technology, but they also say, well, LiDARs are being used for redundancy. Which basically says all pluses and minuses: camera, radar, LiDAR. Green is obviously for good, red is for has problems. Object detection, classification, estimation of distance, velocity, and like you see for yourself pluses and minuses. The fusion would be it. So if you combine all of those, that would be it in order to go for level 3 and up. So if you really want to take out the driver, you need all the sensors that you can get. So camera for color, camera for quick classification of an object, for lanes, radar for bad weather performance, very accurate distance and velocity, and LiDAR really to figure out what exactly is it that I'm looking at, very high precision, and also to work at night, which for instance a camera does not do too well. But the fusion, so combining all these sensors, is really something where the cost we don't really know, and therefore when it's really ready for prime time, we'll see. So let's talk a little bit more about software and also about artificial intelligence. Honestly, I'm sometimes surprised what technologies companies put out there, how to do automated or autonomous driving for that matter, as they call it. Intel, for instance, said, well, relatively straightforward. You don't want to hit someone from behind. I don't know what they talk about hitting someone from the side or head on. Anyway, they say don't hit someone from behind. Don't cut in recklessly. Okay, I agree with that. Right of way is given, not taken. Ooh, okay, that sounds nice. Be careful in areas with limited visibility. Yes, that's a good advice. If you can avoid an accident without causing another one, do it. I don't know. All of this sounds like, okay, 5 rules. I just put them into software and then voila, I'm done with self driving cars. I don't know. Waymo, I got to give them that a little bit better. So when they say, okay, I need to understand where I am, what's around me, what will happen next, and what should I do? And then they say, well, we can figure that out. What this pedestrian is going to do, what the cyclist is going to do. But still, the challenge of actually building a real product is actually more difficult than expected. And that's the former CTO. Actually, he's become co-CEO of Waymo now. Dmitry Dolgov has a great background. I had the pleasure to meet him. Well, it's been more than 10 years ago now. But he really knows his stuff. And if he says, well, more difficult than expected, because these 4 questions, which is different from the Intel example, which is more like an advice how you should do it, but asking these questions, especially what will happen next, that is really, really tough, because this cyclist, is he going to cut in front of that vehicle? Is he going to swerve to his right and basically going around that corner? How can you tell? And a human has a little bit more of a hunch, but also responsibility is actually somewhat distributed between the driver and the manufacturer of the vehicle, which actually does do for different, or does make for different dynamics out there. Because it's really challenging what's going to happen next. In this picture, what do you see? An umbrella, a tree, maybe a person? What do you see here? A cyclist, a pedestrian? That's a difference how quickly objects, people move. What is this? Actually, on a radar scan, same reflection that you would get from a soda can that you would get from a human on the road. And obviously your action, what you should you do next, is very different. There are 2 objects maybe moving at the same speed, about the width of a car, can be 2 motorcycle riders. What about this? You're looking at this with a camera. Is this the road ahead, or is it an advertisement on a truck? Makes a difference how you want to react, what you're going to be doing next. As a human, we can identify this as a stop sign. Can a camera tell this is a stop sign? What about this? A plastic bag flying across the highway. Well, it's a somewhat largish object. Should you brake for it? What about this? Tire debris. That's basically being called the smallest object that you should actually react to. It can be smaller than a plastic bag, but you don't want to run it over because it might actually damage the underbelly of the vehicle, if not more, that it actually might even throw you out of the lane if you hit it in an unfortunate angle. Phantom objects, reflections, shadows, water puddles, all of that. That's where us humans also have difficulty, but we somehow figured it out. Not always, there are accidents, but it is different for a machine to figure that out. And here, flickering light, you know that cameras basically have their frames, they might do 12, 15, 20, 50 frames a second. What if those frames are always right in between when this light is on? You might not see the light at all. A human is different because a human is not digital, not having these frames. So we basically look continuously on analog. So that needs to be figured out. And then really to software a little bit more further. Yes, I do understand that AI is great at many things, including Go. But driving, I find, is different. So what computers are really great at is like to consider a very large number of constellations and rather react to those constellations and complete a mission at very high accuracy and to execute that mission. A human now is very good at an infinite number of constellations. And I think there's a difference between very large and infinity. And humans can anticipate, can cooperate with other traffic participants as opposed to completing just a mission. Humans are creative and have their experience as opposed to just executing what one is told to do. So that's something where how traffic works today, it's very human centric to just put a machine out there to do the same thing. So machine learning is great. It works really very well in a field where rule basis approaches don't. So where you cannot really say if then else, this is where machine learning excels. Where it copes with unexpected situations. But it needs to be trained in this broader field with all these labelings of objects where you say this is a car, this is a car, this is a car. Next time the thing sees a car, it says that's probably a car. And a really large amount of data, obviously. But one should also be mindful of the challenges and pitfalls. It's only as good as the data to train it. And what if you train it in a wrong way? What if it never saw a certain animal and all of a sudden it sees this animal and says, I have no idea what that is. I was not trained to look at it. And it's actually very difficult to test, verify, validate, and certify. And that's what we said also in the flying vehicles that from the FAA, there's currently no artificial intelligence system that gets certified. So it has to be rule-based or deterministic to get certified. And I think AI can do many things for automated driving, but it really should be used responsibly. So gets me to this. So you're all familiar with these recaptures. And if I look at those, I'm like, well, these are all things that I find in traffic. And if these images are used to determine whether a computer or a human person looks at them, does that mean that computers are not good at recognizing vehicles, traffic lights, and crosswalks? It's not very comforting in the idea that self-driving cars being computer controlled keep us safe. So there must be something about it. I'm happy to discuss further, but just keep that in mind. These systems are not perfect, and we still see the limitations every day, if you will. So which gets us to infrastructure. I personally think that infrastructure is really important to bridge the gap here. And actually infrastructure applies to all our beloved ACES topics, whether that's automation, connectivity, electrification, or sharing. You see for yourself here what infrastructure can be like. And you might want to back to this slide. I'm not going to go through all 4 topics. So therefore, let's look at automation. So we need maybe special lanes, special road signs that can be read by a computer readable road signs that might be necessary. A technical infrastructure, which is connectivity that we will talk about in a minute, localization aids, maybe where GPS is not good enough, but also legal infrastructure is needed, with whether that's a permission to operate a vehicle or maybe special uh, rules for traffic, where you say an automated vehicle can do this, but a human driven vehicle maybe not. Yes, it might get messy. That is possible. So us talk about V2X there for a little bit more about this communication infrastructure, which could be essential to enable automated driving, but also difficult to implement because it does require scale. If it's only a few vehicles here and there, you have to get a certain fleet penetration to see an effect just in general. That's just a general rule. If you want to have smartness in traffic, 10% penetration might need to be something to cover it. But still, it requires therefore all vehicle manufacturers, operators, and so on to work together. They all need to speak the same language, otherwise it doesn't work. Cybersecurity, data privacy need to be figured out. And they are actually, there's a spectrum reserved by the FCC here in the United States, but now there's competition actually from internet companies and cell phone companies to use this communication spectrum frequency essentially for other applications, and they are willing to pay for it, whereas well using it for traffic, which has been reserved since the late 1990s, but it's not happening. So we got to see for how much longer we can keep that reserve. But you have to start somewhere, and then it might evolve over time. So to have a blanketed approach all over the country, because to cover all of this up here, that might really be tough. Therefore, huge investments might be necessary. And in the end, you really need to get a pretty broadly deployed network. Otherwise, you get spotty reception and maybe not good enough connection in some locations. And in the end, we do have some connectivity between cars today. We make eye contact, gestures, other cues that we figure out, oh, I think I know what that other vehicle is going to be doing. So that's what we need to get into there as well. So this slide is very busy, I know. I've been trying to simplify this for quite a few years now. I have not accomplished. If you got ideas, please let me know. But what this is, basically all the moving objects, some of them actually also stationary, out there that you want to know about when your car drives itself. So there are other vehicles, pedestrians, road users, animals, objects, maybe a box that somehow dropped onto the road. Obviously, traffic signs, road curvature, all these things, congestion, weather, things like that. And you can tell here what's the distance at which you might want to know that that's out there. Another vehicle, 1 to 50, maybe 100 meters, something like this. Same with animals. Pedestrians are slower, so the distance not that long. Weather, for instance, well, if you know that in 50 kilometers there's going to be icy roads, that's still early enough. And depending on how fast you drive, you basically see here what's the time. It's just a factor between distance and time is speed. What's the time you want to know about it? So if you know 10, 20, 30 minutes in advance that you're getting to an icy patch, that's probably still good enough. Some actually much more detailed, maybe just a few minutes that you know, okay, in the next curve, there's going to be ice. So you get the point. It gets down to milliseconds here for other road users. Guess what? This is where sensors really come in. Sensors cover all of this, where they say what's really near to the vehicle. There's no way you get this from a communication infrastructure. But maybe an emergency vehicle, ambulance car, that sends out, I'm an ambulance car, please go to the side. That would be very helpful actually to send out as a radio signal. But also, if pedestrians had a transponder and sent a signal to the vehicle, that could also be quite helpful. And then vehicle to infrastructure here, where you basically send out weather reports. You send out, I'm a traffic light, I'm going to turn green in 2 seconds. I'm a stop sign, even if you cannot read me, what you saw in the earlier example. So that all is something from vehicle to infrastructure communication that can be done with that and need to get started somewhere. And the last piece I wanted to mention is remote operation. So there's a lot of talk about this, and it might be the missing link to bring highly automated vehicles to the market. What this is really that a human is involved in the operation of the vehicle for communication, monitoring, guidance, and driving via a remote link. So the vehicle is somewhere, maybe in the Bay Area. There's a mission control center that doesn't need to be on site. Same as air traffic control. So that remote operating center can be maybe in a low cost part of the country. Totally possible. And they are connected via a remote link, might be satellite communication, can be fiber optical cable, and then Wi Fi to the vehicle, maybe cellular, needs to be figured out. And so what this is, according to this, your communication, monitoring, guidance, and driving, communication would be to be in touch with the passenger of those vehicles for an emergency, but also general assistance like, all right, we're slowing down a little bit because there's trouble ahead, nothing to worry about. That might be important to communicate with the passengers of a self-driving car. Monitoring, where a remote operator keeps an eye on it, what is this vehicle doing, and might be able to intervene if necessary. Which gets us to guidance, which is more the other way around. Here, for monitoring, the human keeps an eye on it and then interjects, whereas here, the vehicle basically figures out this is a situation, I have no idea what I should do. Asks the operator, what do you want me to do? Stop, reverse, or maybe go around the obstacle. And then there's even remote driving, where you see that the connectivity in terms of latency and bandwidth is obviously absolutely critical to drive the vehicle remotely. Maybe not all the time, maybe only when there's a request from the vehicle. I ask for guidance, and the remote operator says, okay, let me drive you around this construction zone or something like this. And then you are in self driving mode again. So all of that to keep in mind. I know it's quite a bit, but hopefully that gives you some more understanding how a self-driving car works. So there's a lot of technology on board of the vehicle, but also I think infrastructure is really key, and that needs to be figured out as well, how that fits with the rest of the traffic that is very human centric. And I think connectivity, but also better lane markings, road signs, and so are really essential. Gets us to this point. I don't think that we discussed this already, which is something. What's holding us back? What are the big challenges? And I have here first listed with a little blue marker what I think we can overcome. Regulation, I think we can figure that out. Technology, yeah, there's a lot. We just talked about it, but I think we can figure it out. Consumers, some have concerns. Trust definitely is an issue. But typically, once people get in these test vehicles, whether that's Waymo or something like this, after a pretty short time, they like it and they trust it. And rebound effect, we discussed this already in class. It is something we might see more traffic. That's obviously not necessarily what we want, but maybe can be solved on a case by case basis. Maybe incentives, mandates need to be established, but probably we can guardrail that. I think the big challenge, so that's with the two orange markers here, reality. Reality really is it. So how do you mix the current traffic with self-driving vehicles? And this is where maybe a staged deployment is really important. And that's what we see with Waymo. Maybe they have been trying in Arizona for the longest time, now coming to San Francisco. They still have the safety drivers, and I think they better should have the safety drivers. I like this quote here from the CTO from the Audi um, autonomous intelligent driving team. We said getting to 90% is fairly easy. Getting to 95% starts to get interesting, and then you still need to go way beyond that. 9.999, and adding each nine is 10 times harder. When you're at 95%, you've just scratched the surface. So to leave you with this analogy, if you're in San Francisco and you want to go to the top of the world, to Kilimanjaro, okay? So you get on a plane at SFO, you fly to London, change planes, fly to Kathmandu. Okay, you've come very long way already. Then you get to the first base camp, and maybe by distance that's 99, maybe it's even 99.9% or something like that. But then to get to the top from the first base camp, man, this is when it gets really tricky. With this, happy to discuss more anytime. Reach out to me, and I hope that was helpful to get a better understanding what it takes to make a car self-driving. All right, thanks for listening. Talk soon.